Hi folks, welcome to the live session. We're going to be reviewing optimization and then some curve sketching, and then if hopefully we'll have some time to do Riemann integrals, how to do those Riemann sums and whatnot towards the end. So we're going to start with some problems. Hopefully you recognize some of these in terms of the optimization and what's going on here. So how far from A should the point P be chosen so as to maximize the angle theta? Okay, so we have this A, P, and B listed here. You have this length 5, 2, and 6. And so we're going to maximize this angle right here. Will be theta. And so that's going to be our angle that we're maximizing. So in order to do this, we need to find some equation in terms of theta. Well, rather than go for the gusto all at once, what we need to do is figure out what sort of equations can we do to relate to theta, and what are we actually looking for. So you're looking for how far from A should the point P be chosen. Well, so what we'll do is we'll label this distance right here with some variable because it changes depending upon where we place P, and so we'll label that distance x. And if that distance is x, remember this drawing is not necessarily to scale. So what does that mean that distance is from P to B? Well, then we have to be looking at, well, if the distance from A to P is x, the total distance is 5, we just subtract 5 minus x, has to be that distance. Okay? And so now it might seem like we might be one step closer to theta, but notice the triangles here, the two right triangles that we have, theta is not an angle on those. And so what we'll try and do is find what sort of givens can we work with, and can we get to theta somehow, some way? Well, the answer is yes. And what we'll do is we'll label this angle right here alpha and label this angle beta. And so then the sum of these three angles, so alpha plus theta plus beta, well, what should that equal? Well, notice it's a straight line, so that should be 180 degrees. But 180 degrees, remember, we're writing things in terms of radians, so that's pi radians. Okay? And we want to solve for theta at the end of the day, so if we're solving for theta, we get theta equals pi minus alpha minus beta. Now, you might think that's good, but technically we need some more work here, because what we really want to find is this thing, this distance x, right, where we're maximizing theta. So we want to put alpha and beta in terms of x somehow, some way. And so in order to do that, well, let's take a look at beta first. So if we have our angle beta here, and this is 6, and this is x, well, what's the relationship that we have? Well, notice if you take the tangent of beta, that should equal 6 divided by x. And so if we wanted to solve for beta, we need to take basically an arctangent on both sides. So if you have arctangent of the tangent of beta, that should equal the arctangent of 6 over x. So arctangent and tangent, those are inverses of each other, so this just becomes beta equals arctangent, or I'm going to actually abbreviate this now as tan inverse of 6 over x there. So at the end of the day, we have beta, and now all we need is that alpha. So how do we go about getting alpha? So for the alpha, the triangle that we're dealing with there, once again another right triangle, and we had a right triangle here before, and you have a 2 here, but now we have a 5 minus x on this side. And notice the rules pretty much apply the same. You get tangent of alpha equals 2 over 5 minus x. And for those of you paying attention, hearing that weird noise in the background, that might be my dog, actually, kind of talking to me right now. He wants to play. So sorry if you hear any noise outside of here, besides my voice. But so now, trying to solve for alpha, what do we have? Well, same thing. You can take an arctangent on both sides. I'll just kind of cut out that middle step there. So we get alpha equals the arctangent, or tan inverse, however you want to write it, of 2 over 5 minus x. So notice we have alpha in terms of x, we have beta in terms of x, and so now we can rewrite theta equals pi minus, well, alpha is the arctangent of 2 over 5 minus x minus beta is the arctangent of 6 over x. And so first off, let me know if you have any questions. Put them in the chat box for me. I'll be happy to answer those, but hopefully we're all on the same page. If not, just let me know. As I said, I'll try and answer them as they kind of come in. So if we have theta in terms of x, in terms of the optimization, that's our goal. We have the variables that we want, so we have the one variable that we're trying to optimize essentially, and then in terms of the other variable we want to work with, and so just one single variable versus like related rates, you can have multiple variables. So that's the big difference here. We only want the one variable appearing over on the right hand side. So now we can take a derivative, and so our derivative is going to be with respect to the variable x, so we get d theta dx, okay, equals, what's the derivative of pi? Well, pi is a constant, so its derivative is just 0. So we're done with that. So now we're left with negative the arctangent derivative. So if you don't remember, you can look up in some rules of integrals, integrals, I'm getting ahead of myself, rules of derivatives and things of that nature. It goes 1 over 1 plus, and usually it's an x squared, but our x has been replaced with this 2 over 5 minus x, the quantity squared. Now, I'll just write it out for right now as the derivative of 2 over 5 minus x, because we need to use that chain rule. So we'll work with that in just a minute, but that won't be too bad. And then our next term, so minus arctangent again, so we're taking the same derivative rule, 1 over 1 plus whatever's inside the arctangent, we're going to square. So 6 over x, that quantity squared, times the derivative of 6 over x. Okay, so now calculating those derivatives. Hopefully we found out where all this stuff came from, so I'll try and box that off and see if I can fit it in here. In terms of the derivative of 2 over 5 minus x, notice another way to write that, we can pull the 2 out in front, so that's 2 times the derivative of 5 minus x raised to the negative 1 power. So this becomes 2 times negative 1 times 5 minus x to the negative 2. Okay, then times, there's one other thing we got to do, is take the derivative of the inside, and the derivative of the inside is negative 1. Okay, so notice we have a negative 1 here and a negative 1 there. They kind of cancel and go away, and so we're left with 2, and then this 5 minus x raised to the negative 2, this becomes 2 over 5 minus x, the quantity squared. So this whole thing equals negative 1 over 1 plus 2 over 5 minus x, the quantity squared, and then we have times 2 over 5 minus x squared. Okay, with our next one, what's going to happen here? Well, we have the 1 over 1 plus 6 over x, the quantity squared, times the derivative of this. Well, notice this is 6 times 1 over x, so that's just going to be negative 1 over x squared. So that becomes, with the 6 multiplied by that, is negative 6 over x squared. If you have questions on that derivative, just let me know what's going on there. So now, just to make room, I'm going to erase the bottom real quick so we can have some space to kind of finish this thing off. So the rest of this, we've actually done the calculus right now. And actually, the only line of calculus was what we just did in terms of taking the derivative. And the beautiful part here is the rest is just going to be algebra, because all we're doing is setting this thing equal to 0. And then we're going to simplify this a little bit. So 0 equals, what happens? Well, we can distribute that, or multiply that 2 up across the top, so that becomes 2 up there. And then over, when you take 5 minus x squared times both of those terms, you get 5 minus x, that quantity squared, plus, notice this is 2 squared over 5 minus x, the quantity squared. So the 5 minus x, the quantity squareds would cancel in that second term, and 2 squared is just 4. And we have a negative symbol, so this is negative 2 up top. Okay, so now notice on the second term we have a negative with the 6 over x squared and a negative there, so that becomes a positive. Oops. And so on this case, we're going to get 6 over, and then distribute that x squared to both terms. You get x squared plus, well, you'll have a 36 over x squared times an x squared, so that becomes just 36. And so that's our answer there. Now this can lead to the equation. Just move that negative 2 and then that 5 minus x squared plus 4 stuff over to the other side. You get 2 over 5 minus x, the quantity squared, plus 4 equals 6 over x squared plus 36. Okay? So now what do we do to try and solve this thing? It might look nasty, but if you just do a quick cross multiply, so you'll get 2 times x squared plus 36, if that's done correctly. And then equals, what do we have here? 6 times the quantity, 5 minus x squared, plus 4. Alright? So, moving forward from here, where do we go? Well, let's take a look. So to distribute in that 2, we get 2x squared plus 72. And then this should equal 6 times 25 minus 10x plus x squared plus 24. Okay? And with that in mind, we'll have a little bit of distributing over on that right hand side, and we'll have the 2x squared plus 72 equals 6 times 25, so that's 150. So 150 minus 60x plus 6x squared. Well, I wrote the 24 there. Sorry, I got a little ahead of myself. On that previous line, we should have 4 with that last position. I was writing that 24 getting to this next bit. So that's plus 24. There we go. So now where do we go? So moving forward from here, we can get all our terms on one side. So we have the 6x squared. We'll make this all equal to 0 since we have a quadratic. So this becomes 0 equals 4x squared minus 60x. And then let's see here. We have 174 minus 72. That makes what? 102? Is that correct? So this thing should be then plus 102. Okay. So now, how do we solve this? Well, you can use your quadratic formula right away, but it might be one extra step. Okay, so we have a question that popped up. On the part where you set it to 0 and simplify the part above it, how did you get 5 minus x, the quantity squared? So let me make sure I'm getting the right spot here. Where did I get the 5 minus x, the quantity squared from? Is it in this line that you're referring to, where I started? So yeah, just let me know if that's the line where you're referring to. What we had to do is take this 5 minus x squared and the line up above it. We multiplied it times that term, and then we multiplied the 5 minus x squared times the other. Okay? So notice that 5 minus x squared times the 1. So that goes, and we have a 5 minus x squared there. So now let's write this. I'll see if I can fit it here. So we have 2 over, for the second term, 5 minus x squared, and we have a 2 squared, and then this is all times 5 minus x squared. And so for the second term, notice this term and this term will cancel, and you're left with 2 squared, which is 4, and that's where this 4 comes from right there. Okay? Hopefully, if that answered the question, just let me know. If it didn't answer the question, let me know, and I can elaborate a bit more if I'm on the right line. In terms of just moving it over, so that next piece right there, what did we do? We added the 2 over the quantity 5 minus x squared plus 4 over to the other side. And so that's why we had the positive. So hopefully that makes sense in terms of what's going on is where the 5 minus x, the quantity squared, came from. If not, as I said, just let me know and I can try and elaborate a bit more and go through those steps in between as well. Hopefully we're kind of on the same page as to where the equation came from at this point. I'm going to race to the left hand side because we're going to need that space in just a minute. So kind of filling in some stuff here, and you can see some of these problems get pretty big pretty fast too. So seeing no more questions, hopefully that answered it. Now where do we go from here? We want to use the quadratic equation. If we go and try and solve this thing, we might want to notice you can factor out a 2 pretty nicely from each term. So we get 2, and then you'll have a 2x squared, and we factored out that 2, and then minus 30x, and then plus a 51 right there, I believe. Okay. So now we can use the quadratic formula. Divide both sides by 2, and you'll have 0 equals just 2x squared minus 30x plus 51. And we can use the quadratic formula. Quadratic formula, if you recall, it goes x equals negative b, which is, I'll sing the song actually if you'd like. The Pop Goes the Weasel song, you can always kind of remember it. It goes negative b plus or minus square root b squared. Oh, that square root's awful. So let me try to start that over. Negative b plus or minus square root b squared minus 4ac, and your a is 2 and your c is 51, all over 2a, and a is 2 once again. So we have all our values there. Hopefully you enjoyed that singing. Don't expect it anymore. So going from here, 30 plus or minus, we get the square root of, well, what's going to happen? 30 squared is 900 minus 4 times, well, yeah, you can do 2 times 51. That's going to be 102, and then 4 times 102 is going to be 408. And then all this is going to be over 4. And now is when we need to think about what's going on. In terms of our solutions, think about the range of x values. Well, notice in our original problem, and we could have found the domain right out the gate too. Some people like to do that. I like to kind of wait till the very end. Honestly, it's your preference. But the range of x values here is 0 to 5. And why is that? Well, notice we have a whole length of being 5. So if we exceed 5 for our x value to place the p, we've exceeded the values of where the triangles can exist. So we have to have it at least 5, and then 0 at the bottom end. Notice if we go to the negative numbers, we're going to run into a problem there as well. So that actually plays a role in terms of what we're doing. Because notice this 900 minus 408, that's going to have a square root of 492, I believe. And so we'll have 30, and then most people will say plus or minus. Well, I'm going to wait a second before we fill that in. 30, now let's think if it was plus square root of 492. And if you're wondering where square root, and I understand there's no calculators that I allow and all that stuff, but just get a ballpark feeling as to where this square root of 492 lies. First off, 20 squared we should know, right? So you get 20 squared is 400. So with that being 400, we know that the square root of this number is larger than 20. Square root of 492, since it's larger than 400, has to be larger than 20. So right out the gate, if we added these two values, we're going to get a number that's larger than 5. So that tells us the only possibility here is subtraction. Now, to be a little bit more specific in terms of making sure it fits inside these values, let's see. Let's do, what is 22 squared, right? 22 squared, I believe that's what? Oh, do 20 squared times 20 squared is 400, and then you can do the the FOIL method, right? So 2 times 20, 2 times 20, so you get an extra 40 and another 40, and then 2 times 2 is 4, so that's going to be 484. In a similar manner, 23 squared, what is that? You can do something similar there, so you get 529. Okay, so now we know this number, square root of 492, is somewhere in between 22 and 23. Okay, so with that in mind, if I go 30 minus, let's say 22, so that's 8 divided by 4, and if I went 30 minus 23, that's 7 divided by 4. Either way, I'm kind of in that 1 to 2 range, essentially. So we'll put it over here. In this number that we're going to check, so 30 minus the square root of 492 all over 4. We know that when we plug this into d theta dx, we're going to get 0. Now the nice part is we can plug this into d theta dx, and the best place to probably plug this in, the most simplified form, is actually where you see that star, okay, or that asterisk over on the side. Not the one on the right, but the left-hand version. So I'll put it next to the 0. So we'll put a star here. So if we plugged in, say the number 0, for example, we can figure out if it's negative or positive to tell us if it's increasing or decreasing, because we're trying to maximize. So hopefully, if things go right, this is going increasing to decreasing. So let's plug in 0. Notice you get negative. Notice we have a square on the bottom. So regardless of what's going to happen, we're going to have a negative, but we're adding here, so we got to be a little bit more careful than that. So in the first case, what will happen? Well, we'll get negative 2, and then you'll have 5 squared plus 4, so that'd be negative 2 over 29. Plus, and then it'd be 6 over 36. So notice this number is 1/6. This number, you could say, essentially, we're trying to see, is it bigger or smaller than 1/6? Well, notice if we had negative 2 over 12, that would be equal to 1/6. Since it's negative 2 over 29, that's going to be a smaller number than 1/6. So we know that this value is going to be positive. Okay. For the other value, let's see if we can make this work out nicely for us. Let's plug in 5. What happens? Well, if you plug in 5, notice we get negative 2 over 5 minus 5 would equal 0 squared plus 4. So negative 2 over 4 plus, plug in 5 to the other one, you get 6 over, we would need this to be 12 in order for it to match. Notice right out the gate you get 25 plus 36, so that's going to be 61. That's not even close to 1/2, so this is going to be negative. So it goes from increasing to decreasing. So increasing to decreasing. And what does that mean? Well, that means this has to be a maximum. Okay, so how far from x should we choose? Well, we should choose x equals 30 minus the square root of 492 all over 4 for our value. Now that might not be so obvious, and I chose some numbers that might be a little bit more difficult here. If you want to work with some numbers that are easier, you can start messing around with your, rather than having 6 on one side and 5 on the other, you can mess around with those numbers. The process is the same, but you can still come up with an answer, and it might be a nicer number. The square root might come out to be a much nicer square root where you get a nice solid answer. So keep that in mind. If there's any questions on this one, just let me know. As I said, I'm happy to kind of help out. That's what I'm here for. That's my main purpose. So on our next one, the Norman window problem. So this is kind of notorious amongst calculus communities here. These Norman windows, what do they look like? I don't know if you've ever been to, say, a place where there's a lot of stained glass or whatnot, but you get these Norman windows that look something like this. Okay, and so what we want to do on this Norman window, so you have a rectangle on top of a semicircle, and so I'll put this little dotted line here. Okay. Suppose the outer perimeter of such a window must be 1,000 centimeters. We want to find the maximum possible area of the window. So other ways you might hear this is what window would allow the most amount of light in and things like that. So at the end of the day, though, what we have is there's a couple ways to approach this, and I'll show you, and we'll kind of break this apart. If we have this being x right here, that means this is x, and then we have a nice little equation we can set up. Let me put L right here. Now, one thing that we can think of is the area is what we want to maximize. So area of this whole thing is going to equal, first off, let me give some shorthand notation. It's going to be the area of the rectangle plus the area of the semicircle. Okay, according to this drawing, what's the area of the rectangle? Well, it would be x times L. Or I could put a W in here or an R in here. Whatever you really want to use is fine. And then plus, notice if x is that distance, we're going to have the area of a semicircle. So it's, first off, the area of a circle is pi r squared. Well, r is going to be 1/2 of x, because x is the full diameter, so 1/2 of that. And then, so pi times 1/2 x, and then we square that quantity. But then, on top of that, we only want half of that area, so we go with half there. Okay, so now with that in mind, we have a few too many variables. And we can work with it and try and brush it on down. But there's actually another route here if you're making your labels. Something to keep in mind as well. What I would recommend, you see this 1/2 right there and the 1/2 right there. That makes this nasty right out the gate, at least in my eyes. I'm not saying it has to be that. You might like the halves and working with that, but I'd probably, personally, I'd rather solve the problem to make it a little bit easier on myself in terms of the math involved. And so that's what I'm going to do here. I'm going to make an adjustment. If I, rather than have x be that whole distance across, I'm going to take x to be the radius, essentially, of that semicircle. So if x is the radius, notice, what is that whole distance across? Well, that makes this 2x all the way across. So that's going to change our formula. And that's just setting it up. And that's fine. We can start to work a problem to make it a nicer equation for ourselves. Not saying you had to do it this way. If you prefer the other way, just let me know. I can work it out the other way. You're just going to have a little bit more difficult things to work with algebraically at the end. So notice our area of our rectangle in this case would become 2xl, and then the area of our, we'll still have a fraction, but it won't be quite as bad. Area of our semicircle will be 1/2 pi, and then notice it's just x is our radius, so it's pi x squared. And that's a lot easier to deal with, personally, at least from my eyes. You might feel differently. If you want the 1/2 x to be that quantity squared, that's fine. We can work with that too. But at the end of the day, we're going to find this area. But the problem point is we have this L right here. So can we solve for L? And that's where we try and look for some given condition to get rid of that extra variable. So our given condition is the perimeter of a window is 1,000 centimeters. So first off, perimeter here, what would that be? Well, notice if it's just our length around. Okay, so you start with the L, then you go with 2x. So we're going to go L. So if we had a starting point maybe right here, you go down, you get L, you go over here, you get 2x. So we'll put plus 2x plus another L when we make our trip back to here. Now we aren't going on the inside, we're staying on the outside because it's the perimeter. So we want to get back to our starting position. So if we were starting right here, what's the distance on a semicircle? Well, that's the circumference of a semicircle. And so the way we get that is usually it goes 2 pi times the radius. So that would be 2 pi x, but we don't have a full circle. We have a semicircle, so that would be 1/2 2 pi x. And that's once again the reason why choosing x to be the radius, our lives are going to be a little bit easier. So moving forward from here, what do we have? Well, we have 2L plus 2x plus pi x. And what does all that equal? Well, that equals, remember the perimeter is just 1,000 centimeters. So 1,000 equals 2L plus, and then I'm just going to group the 2 plus pi together times x, because x was a common factor of both of those. So now we can solve for L. So you get 1,000 minus our 2 plus pi times x equals, now we could put 2L, but I'm going to put L, and the way we solve for that is just divide both sides by 2. Okay. So we have a question along the way, and this is good. So the way I'm approaching this problem might be different than what you're trying to solve. Say you're working on a homework problem. I'm trying to illustrate a couple different ways. So why is the bottom, so here's the question, why is the bottom width 2x instead of just x? So I could call it x, but the formula up top is going to be a little bit more nasty in terms of the fraction. And in fact, when we had pi times x, you'd actually have 1/2 pi times x in this case. But what we did is we made a change. This x, and I'll write it in here, this x we're going to have be the radius instead. If you want to have that be x, you can solve it accordingly. Or if we solve for x in here, where x is the radius, just remember, at the end of the day, we'll just multiply it by 2 because it's the diameter. So that's all that there is to it. So because if you look here, here's an x, and then the radius is just the center of the circle to the outside of the circle. So another distance here would be x. This is also a radius. And so x plus x gives us 2x, and that's why we have the 2x down there. Hopefully that makes sense. If not, just let me know. Let me know. Put up another question, and I'll try and answer that as well. So yeah, keep those questions coming. That's my main reason for being here. So I'm glad you're all asking them. Now, looking at our area equation, let's see what happens. So our area, we want to get it all in terms of x. So we have 2x and L. What the heck is that thing? Well, notice you have 1,000 minus, and then in parentheses 2 plus pi x, and then divided by 2, and then plus a 1/2 pi x squared. Okay, it looks scary. It's really not that bad though at the end of the day, because notice your 2's will cancel, and this x we can even distribute on through. So we get a equals 1000x minus 2 plus pi, and then x times x will give us x squared, rather than multiplying 2x plus pi x. It's easier to just have that x squared on the outside. Plus 1/2 pi x squared. Okay, and we could incorporate that 1/2 pi x squared in with this x squared term, but it's really not, well, it's up to us at the end of the day whether or not we want to. It's not going to be too bad either way. Right now we're ready to take a derivative. So taking a look at this, let's just take a derivative and get this show on the road. So dA dx, what does this thing equal? So the derivative of the first term, notice just derivative of x is just 1000. The 2 plus pi is just a constant. So we'll put 2 plus pi, and so derivative of x squared is just 2x plus 1/2 pi, and derivative of x squared we just talked about is 2x. So really, there's our calculus right there. That's the only line that really does it in terms of the calculus. The rest is just algebra, and that buildup was mostly just setting up so we could apply that one derivative. In terms of now what we're doing, we set this whole thing equal to 0. So you get 0 equals, we have 1000. Now let's be careful here. We have the x's, got a 2 that we can multiply, so you get, and now I'll be writing this as 4 plus 2 pi, that whole quantity, and then times x, we distribute that 2 on in, and then plus 1/2 and the 2, those things will cancel off, and we're left with plus pi x. Okay? So making this a little bit nicer, we'll get 0 equals, well actually we'll do that in another step. Just so you all can see the algebra, I'll just wait 1 second, not do too many steps at once. So 1000 minus, we have that quantity 4 plus 2 pi, but so notice that goes minus 2 pi essentially, and we have a plus pi. So if you have minus 2 pi x and then plus a pi x, notice that's going to lead us to a minus pi x. But the way we're writing this is 4 plus pi times x, because that minus sign is distributing. So now what we can do is just add over that term. The 1000 is going to remain on the other side. So you have 4 plus pi times x, and that equals 1000. So if we want to solve for x, what does x have to equal? Well, divide both sides by the 4 plus pi, and we have our solution. Now, does that mean it's a maximum? No, this might be a minimum, so that's where we have to do some checking. And I'll try and see if I can fit it here. So first off, what's the smallest value x could be? Well, you really can't hit the value, but you could have x be approaching 0, right? So a really thin, or I should say tall window, essentially. Extremely tall, but not very wide at all. So we can approach 0, but never really include it. And then you can go any sort of width that you want, as long as we still have that perimeter holding. So the only caveat here is we're going to have 1000 divided by 4 plus pi up here somewhere. And up top, so these are your x values, and we're going to kind of keep on going. Those are your x values, and then we're looking at the derivative of a with respect to x. And so we know that that equals 0 at that one point. And so let's try and get a ballpark idea as to where that value lies. So this thing, notice in the denominator, 4 plus pi, pi is 3.14159, so it's a number between 3 and 4. Right, we don't have to be so specific, but just if it was 3, you'd have 1000 divided by 7, right? And if it was 4, essentially, you'd have 1,000 divided by 8, right? Let's kind of get a ballpark idea, maybe on the 1,000 divided by 8. Notice you can write that as, so 8 divides in perfectly, by the way, so we'll have 125 is what that value becomes. So we're pretty gosh darn close with 125. And then with the 1,000 divided by 7, we can go through that calculation as well and try and figure out what's happening. But ballpark idea, we're in the range of 125, right? So now we can work with that. And so a number to probably plug in and check with, when we've calculated our derivative, remember our simplified formula was 1,000 minus 4 plus pi, that quantity, times x. That's the one we should check to see if it's negative or positive. So if you plug in, let's say x equals 1, that'll be part of our first test interval. So when we plug in 1, notice you get 1,000 minus the quantity 4 plus pi. Well, shoot, if we do that, just the 4 plus pi times that, notice you're going to get 1,000's a much bigger number than that. So you have a positive sitting right there. In terms of the other values, let's pick a number larger than 125, essentially. Just to make sure. We could do 125, but at the end of the day, that should do the trick. So let's pick the number 1,000, for example, because that's somewhere over in this interval. So if we go 1,000 minus 4 plus pi times the quantity, that whole quantity times 1,000. Notice that has minus 4,000 right out the gate. 1,000 minus 4,000, that's going to be a negative number. So that is a negative number. And we find that that won't give us, we have the functions decreasing. So that won't give us the opposite of what we're looking for. It gives us exactly what we're looking for, from increasing to decreasing. So that means this value right here is a maximum. But does that finish the problem? Well, no, not quite, actually. What we need to do is we want to find the maximum possible area, right? So going back to this line, I'll start right here. What happens? Well, we got to plug in. Oh, actually, I'll go one line down. It's a simplified form. Got to plug in for x. Okay, what are we plugging in? We're plugging in 1,000 over 4 plus pi. So our final answer, so I'll write it up here. Actually, let me do this. So final answer is 1,000 times 1,000 divided by 4 plus pi. And then minus, well, we have 2 plus pi times 1,000 over 4 plus pi, the quantity squared. And then plus 1/2 pi times 1,000 over 4 plus pi. We can leave our answer as that. You can actually do some canceling too, just an FYI if you wanted to. It's not necessary, but you see how you have the 1,000 squared here. You have a 1,000 squared over 4 plus pi, that quantity squared. You can do some simplifying, get some common denominators, and work from there. But this, for our final answer, works out just fine. And if we wanted to figure out what that exact number is, we could have a calculator, but as I mentioned before, we aren't allowing calculators, so this is what we leave it as. Okay. Hopefully that makes sense on that problem. As I said, Norman windows, you see them all the time. Every calculus class, it's kind of the standard optimization problem that people like to work on. So, all right, moving on to one more optimization. This one, for some reason, freaks people out, and so we'll talk about it, try and get a nice answer for it. So the blood vascular system consists of blood vessels that convey blood from the heart to the organs and back to the heart. The system should work so as to minimize, so we're hopefully going to be minimizing things today, the energy expended to the heart in pumping the blood. In particular, this energy is reduced when the resistance of the blood is lowered. And hopefully I can pronounce this right. One of Poiseuille's laws gives the resistance R of the blood as R equals C times this fraction L over R squared, where L is the length of the blood vessel, R is the radius, and C is just some positive constant determined by the viscosity of the blood. So the figure below shows a main blood vessel with radius R branching at an angle theta into a smaller vessel with radius S. Determine the value of theta that minimizes the resistance, and so our answer could be in terms of A, B, R, and S. Let's try and tackle this problem. Okay, the key is that L is the length. Okay, and so let me see if I can get up a new color here. Let's go back to black here. So at the end of the day, when we're looking for length to be involved, recall we have the formula already. R equals C times L over R squared, where this though is the radius of the vessel. Don't confuse that with the R here and the S here. They're two different vessels. We're going to have to work with them. Okay? So we want to minimize the resistance kind of going up this blood vessel. So how do we do that? Well, first off, the C is going to be pretty much consistent throughout. So we have R equals C, but times this whole quantity, and let's talk about that a little bit more at length. So we have R squared is going to appear on the bottom in the first case, right? Because that's the radius of the first vessel. But then we're going to also have to calculate another vessel, and that's going to be, so the first one is with the R squared. We're going to be looking at this length. And we'll call that L1. And then the other one, we're going to have to figure out this length. And we're going to have to call that L2. Okay? Well, how do we figure out L1 and L2? So the first case we'll say is C, and then we'll have L1 over R squared. Second case is L2 over S squared. Oops, S squared. Said it right, just didn't write it right. Okay, so we got to find L1 and L2. And the only other thing that we have involved is theta. So we want to find this angle theta that does the trick for us. Well, let's talk about L1. First off, if we can find the distance here, let's put a question mark. Notice L1 equals, we can go A minus question mark, right? And the A is some constant we can have as a value there. So if we can find question mark, we're in good shape. Well, what's the thing that relates theta, B, and question mark? Well, you can usually say question mark. Well, let's do it this way first. So the first guess, what most people find is they'll say, hey, I know that tangent theta equals B over question mark, right? But we want to solve for question mark, so that means question mark equals B over tangent theta. And if you're real good with trig functions, you could recognize right away what happened there. So your question mark equals B times, well, 1 over tangent theta is just the cotangent theta. Okay? So another way for us to have written this equation is C times this quantity. So L1, remember, it goes A minus question mark, and our question mark is B cotangent theta. And then that's all over R squared. So hopefully you all saw that triangle that we're working with there. If not, let me know. And then we're going to work with that triangle once again. So that theta can help us find L2. So for L2, we're going to use, once again, B and theta. Since that's just a distance straight away, let's see what we can find. So using B and theta, what's the relationship? So most people will say initially the sine of theta equals B over L2. But usually we want to solve for L2, so it's better to have the L2 in the numerator there. So L2 over B, what is that? Well, that's going to equal the cosecant of theta. Okay, so that means L2 equals B times the cosecant of theta. So therefore we have plus B cosecant theta all over S squared. Now we might be asking, what's the variable here? Well, A is some constant. It's some constant length of this vessel. B is some constant. It's some height of the vessel, right? R is some constant. It's some radius of the first vessel leading into the smaller vessel, S, right? So the only thing that's the variable here is theta. And that's a beautiful thing, because now we have R equals some function A minus B cotangent theta over R squared plus, well, actually let me write this slightly differently. For the derivative's sake, we'll make our lives a little bit easier here. Let's break it into A over R squared, and keep in mind A and R are just constants, minus B over R squared times cotangent theta. That'll probably be a little bit nicer for us in a second. Plus B over S squared times cosecant theta. Now where the heck do we go from here? Well, if we've done things right, we should be able to take a derivative now in terms of theta. So this leads to dr d theta equals, well, the constant is going to stay out in front regardless, so we'll have that constant there, right? So you have constant times A over R squared. That, remember, both of those terms are constants. Derivative of a constant is 0. So you get 0 minus. So minus B over R squared is the constant. We can pull that out in front. The derivative of cotangent theta is negative cosecant squared of theta. And then the derivative, we have, for our next one, B over S squared. So that'll remain as is. And then derivative of cosecant theta is negative cosecant theta cotangent theta. So, and this is what freaks a lot of people out, is you see all these A's, B's, R's, S's. Most of that stuff is constants. The only thing that's a variable here is theta. As soon as we figure that out, life is good, right? So now moving forward from here, how do we do this? Well, we set this thing equal to 0. So 0 equals, and notice we could divide both sides by c right away, so actually the c isn't even going to matter. You have a negative times a negative, that'll make a positive in that first case. So you have b over r squared cosecant squared of theta plus, or actually I'm sorry, minus, we'll distribute on through, b over s squared cosecant theta cotangent theta. Alright, so now let's move that minus part over to the other side. When you get to trig functions, it can be kind of tricky. So b over s squared cosecant theta cotangent theta equals b over r squared cosecant squared theta. Now here's something we can notice. You have a cosecant theta appearing on both sides. So you can divide both sides by cosecant theta. We can also divide both sides by b. And so what does that leave us with? When you divide both sides by b, notice the b on the left-hand side is gone, so you're left with 1 over s squared. And we talked about dividing both sides by cosecant theta, so you're left with 1 over s squared cotangent theta. And that should equal Divided both sides by b, so the b is gone, so you're left with 1 over r squared. And then we divided both sides by cosecant theta, so one of those terms crosses out, and we're left with just 1 cosecant theta there. So now we're trying to solve for theta, so we probably want to get all our theta terms on one side. And the way to do that, divide both sides by cotangent theta and multiply both sides by r squared. So we'll left with r squared over s squared equals cosecant theta. Whoop, did not mean to do that. Cosecant theta over cotangent theta. Now this might be a place where you want to try and write things in terms of sines and cosines. So r squared over s squared. Oh, I probably should have went the other way. It would have been a nicer trig function. So this is 1 over sine theta over cosine theta over sine theta. And so what we're left with is r squared over s squared equals 1 over cosine theta. Some people don't like that cosine theta listed that way in the denominator. You could write it as secant theta. It's that simple, and do an inverse secant. But we can flip that upside down, and it won't only take us a second. You get s squared over r squared equals cosine theta. And we're trying to solve for theta at the end of the day. So theta equals arc cosine of s squared over arc squared. And why can we get away with that? Notice we need an arc cosine to be defined. It has to be some number between -1 and 1. We know s is the smaller of the two radii. It says somewhere in here. Yeah, in the smaller vessel with radius s. That's the reason we know that this is going to be defined. And you can do the check and make sure that this answer works. Remember, you can do the number line. I'd plug in 0 into your equation for the derivative and just see, hey, what happens when we plug in 0 or approach something close to 0, what's going to work out. But so at the end of the day, this is actually going to work to be the one that minimizes the energy expended. So hopefully that makes sense on that problem. I know it caused a lot of confusion along the way. So, all right, I think we're ready to move on forward into curve sketching. So sketch the graph of the curve f of x equals the cube root of x cubed minus 3x. So before we even get into the derivatives and all that stuff, we can start talking about domain with a curve. So domain, notice this is a cube root. So since it's a cube root, you can have both positive and negatives underneath the root. And since we have a polynomial, we have nothing to worry about. There's no fractions or anything like that. So the domain, first thing, we have negative infinity to positive infinity. That's good. So we're good there. Intercepts. There's another thing we can check. Okay, so when is this thing equal to 0? Well, what happens? Well, first off, we'll start with the y-intercept. Remember, a y-intercept occurs when x equals 0. So when x equals 0, notice we get f of 0 equals 0 cubed minus, oops, let me put a cube root there, minus 3 times 0. And what are we left with? This whole thing equals 0. So you have the y-intercept occurs at 0, 0. That's good. So now the other one, x-intercept, or possibly intercepts, because you can have more than one. Notice even with the cube root, you're setting the whole equation equal to 0, so it's when the y value equals 0. So you get cube root of x cubed minus 3x. So in order to do that, we're going to have to, first off, you can end up cubing both sides and you get 0 equals, let's factor out the x here, so you get x in x squared minus 3. So what's happening with that? Well, you're left with this is x equals 0 or x squared minus 3 equals 0. In the second case, you're left with x equals plus or minus the square root of 3. And so now we have the x-intercepts. If we're actually drawing a graph, that tells us some points we can put on there. So let me actually set up the graph. We'll do all the graphing on this page. So when we're going to graph this thing, notice we have the point 0, 0. So we'll actually put this in blue. And so marks 0, 0. And then we should also have square root of 3, 0. And negative square root of 3, 0. And I'm going to hold off just slightly before I put those values in, because how we'll label the axis will depend upon what's happening. The 0, 0, that's not going to change. It's always going to be the origin, so there's no big deal there. So let's go back real quick and try and find some more information. So what's some more information that we can deal with? Just the graph itself. Well, you can find the infinite limits. And notice we don't have any asymptotes or anything like that because the domain's negative infinity to positive infinity. If not, you have to check other limits and things of that nature to see how the graph goes. So limit as x goes to infinity of cube root of, rather than write x cubed minus 3x where we get infinity minus infinity, I'm going to write this as x times x squared minus 3. Okay? And that way we can kind of see what happens. Keeping tabs on this. So notice when we plug in, we get infinity times, this becomes infinity here. So infinity times infinity, even if we're taking a cube root, that's going to approach infinity. Okay? And then on our other case, limit as x approaches negative infinity, what's going to happen? We have cube root of x times x squared minus 3. Let's think of it. When we plug it into x, that's going to be negative infinity. When you square it, though, it's going to become positive infinity. Negative infinity times positive infinity will equal negative infinity. Okay? So now we have the infinite limits. So as we approach, let's put that off on the side here. So limit as x approaches infinity of f of x equals positive infinity. Limit as x approaches negative infinity of f of x equals negative infinity. Okay? So there's some more information for us. Now, moving back to this. So I think that's it for our domain and intercepts, and you can talk about range, but that's not necessary just yet. That'll come to fruition here in a second. But actually, we already have an idea if we're approaching negative infinity and positive infinity. So the next piece that we're going to need is to use the derivative. So f prime of x equals, notice you get 1/3, what would that be, x cubed minus 3x raised to the negative 2/3 times the derivative of the inside, which is 3x squared minus 3. Now usually I'd say you don't have to worry about simplifying, but in these cases I would. And to kind of give you a reason why, notice this thing can be factored out. You have 3 and then you have x squared minus 1. So the 3's would cancel. This becomes a cube root of x cubed minus 3x, that whole quantity squared. Then what do we have? Well, we have x squared minus 1 up top, which we'll deal with in a second here. So what we want to find next are critical points. So the critical points are when this thing is either undefined, or this derivative is undefined, or equal to 0. So let me write this. You can actually factor the top. I'm not saying we have to, but it might be a little bit easier for us. And just so we know, on the denominator you have x, And then remember, this is x squared minus 3. Okay, and we square that whole quantity. So first off, when does f prime of x equal 0? Well, that's when the numerator is equal to 0. So when we already have it factored, x plus 1 times the quantity x minus 1 equals 0, which is x equals plus or minus 1. Okay, so now with that in mind, we can find some values. So let's plug those back in to our original function, f of 1. So f of 1, what do we get? We get the cube root of 1 cubed minus 3 times 1. So it's going to be the cube root of negative 2. Or we can also write that as equal to the negative cube root of 2. F of negative 1, on the other hand, that's going to be cube root of, we have negative 1 cubed, which is negative 1, minus 3 times negative 1, so that's going to be plus 3, so that's going to be cube root of 2. And that's our solution. So there's a couple points that we're going to have involved. And then other critical points that we're going to have to consider. F prime of x is undefined. Well, notice that's going to occur when 0 equals the cube root of the denominator, x cubed minus 3x, that quantity squared. Notice though, we can get rid of the cube root and the square. It's basically the x cubed minus 3x. We already know these values. We already solved for this. So this occurs when x equals 0 and then plus or minus square root of 3. Right? So with that in mind, we actually already have some of those values, but we can now start to display these a little bit better. By the way, let's talk about this a little bit more. So square root of 3, so the positive version, where's that between? Well, notice if you square 1, you get 1. So that means this thing has to be greater than 1. If you square 2, you get 4. So this thing has to also be less than 2. And in a similar manner, you have negative 2 is less than negative square root of 3, and that's less than negative 1. Okay? So keeping that in mind, let's compare that to, well, we have values, the 1 and negative 1. So we have some places that we can place this on our number line. And so personally, what I like to do when we're drawing the graph, we're going to find intervals of increasing and decreasing. And so let's go over here and talk about that. So we have 0. Remember, we're going to have 1 and negative 1 as critical points. And then we're going to have square root of 3 and negative square root of 3. Okay? And then we also had, if you recall, we had 1 came out to be, I believe it was negative cube root of 2. That's going to be on our graph. And then we had negative 1 was going to spit out positive cube root of 2. Those are points on our graph. If we are taking a look at f prime of x equal to, we'll put it in that factored form that we had in the previous page, x minus 1 times the quantity x plus 1 all over the cube root of, we had x, and then I believe it was x squared minus 3 is what we had. These are our x values. We know that for the negative 1 and positive 1 we get 0. For when x equals 0 we get a does not exist, square root of 3 we get a does not exist scenario, and negative square root of 3 we get a does not exist scenario. So we have a whole bunch of intervals that we're going to have to check and see if this is positive or negative. So the first interval, the test interval that we'll look at, is from negative square root of 3. If you start at negative infinity and go to negative square root of 3, that's our first test interval. And remember, we already talked about this. Numbers that we can plug in. 2, for example, would work for us. And by the way, we're squaring the denominator. So when we're plugging this in, we don't even have to check the denominator. Okay? So keep that in mind. The denominator is always going to be positive. So all we need to do is check the numerator. Pick a number in between here. -2, for example. Remember we said would work. So when we plug in -2, you get a negative on top and another negative here. Negative times a negative makes a positive. And so that we have positive. So it's increasing on that interval. Now, for our next one, we got to pick a number. And this might be a little bit trickier for most people. We're going between -√3 and -1. Well, you might not be so sure, but until you go to -√2. Notice that has to be between because it's smaller than -√3, or I should say larger technically because we're going left to right on the number line. But it's not quite the same as -1 because that would be -√1 essentially. So -√2 will plug into here. Notice when we plug in -√2, you're going to get a negative in the first term, and you're going to get a, well, when we go, that's a number slightly less than -1, so that's going to be a negative as well. So negative times a negative makes a positive once again. So we have another increasing interval. Now moving forward between -1 and 0, let's place on this interval, let's choose as a checkpoint maybe -1/2, -0.5. So notice we get a negative here, and then -1/2 plus 1, that's going to be a positive number. So negative times a positive is a negative. So that's how we get that value. Moving forward from this part, between 0 and 1 is our next test interval. So that means we got to check 1/2. When we check 1/2, or it doesn't have to be 1/2, it could be 1/3, 1/4, but check 1/2, you're going to get a negative here, and you're going to get a positive. Once again, negative times a positive is a negative. So we have the negative going on right there. Next place, between 1 and √3. So let's once again go √2. Notice in this case we're going to get a positive and a positive, so that makes this positive. Alright, and finally we go from √3 to positive infinity. Pick 4 if you want, and notice that's once again positive and a positive, so that makes this a positive, so we have increasing intervals. So we're ready to go there, and I'll erase these intervals. We kind of have an idea as to what's happening there. And where do we go from here? Well, we're ready to set up our graph in terms of plotting those points. We already have those placed. So we had a couple other points that we needed to put on here. So let me put those in blue. Okay. So notice we'll have -1 line up right here, -√3. I'm not saying this is necessarily to scale in terms of the little dots, but it gives us a gist as to what's going on. So at 1, we want a -√2. Notice that's going to be a number slightly less than -1. So if this is -1 right here, we want a number slightly less than that. So we'll put that dot right here. Similar manner, we're going to have √3, 0. That one's going to be easy. We can plot that right there. And -√3, 0. So for -1, we want it about equidistant as to what was happening at +1. So we're going to have something looking like that. Okay. Whew. A lot of work, it seems. Now we're on to the second derivative. So second derivative time. First, let's calculate that. So let me write that maybe down here. F double prime of x. Notice the derivative we'll start to work with is the derivative of the derivative. So let's work with this one. I think that might be the easiest one for us to see what's going on. First thing you do, we can use a quotient rule if you want. It's not necessary. Actually, you could use a product rule. Just write it as something to the -2/3 and work with it that way. That'll work as well. But so, just to keep it simple, let's use that quotient rule. So we take this cube root of x cubed minus 3x, and you take the quantity squared and square it. That makes it to the 4th power. Okay. Derivative of the numerator, you get 2x, and then we have a cube root of x cubed minus 3x, and then that quantity squared. Minus, now the fun begins. So we got it to the essentially the 2/3 power, so that's going to come out in front 2/3, and then it's x cubed minus 3x, and when we subtract 1, that should be a negative 5/3, I believe. Okay, and so with that in mind, what do we have? All that's, we got to take the derivative of the inside, so we get 3x squared minus 3. Once again, that'll start to cancel, and then we have an x squared minus 1. Okay. Wowzers. Let's see here. So you can do some razzle dazzle in terms of getting a common denominator. Depends how much time you want to take. At the end of the day, to kind of brush up some of this real quick, you can start to see this becomes a value in the denominator, this x cubed minus 3x to the negative 5/3 and all that jazz. So you can actually start to get a common denominator with those terms and then try and cancel some things out. You're going to have a whole bunch of stuff cancel out. Just like we had the 3x squared minus 1 here, the 3's will cancel. You're having a 2, you have x squared minus 1, the quantity squared. Luckily you'll get an extra factor of that appearing down below. And so what's going to happen at the end of the day, just to kind of brush up, and if you want to see all the extra steps in terms of how to brush this up, I'm happy to do it too. You should get negative 2x squared minus 2, and then it should be something x cubed minus 3x to the 5/3. Alright, that's what it should brush up to be. And you can kind of see what's happening with that negative 5/3 there. That's going to go down to the denominator and take over, essentially, what's happening. And just a little bit of practice there. So now, the numerator, you can factor a little bit. So that's negative 2. Then you get x squared plus 1, which will be important for us to recognize. And then this 5/3, remember that's cube root of x cubed minus 3x to the 5th. And so what we have is f double prime of x squared plus 1 can't equal 0. Essentially, it's only equal to 0 if you have I or negative I, but we're just talking real numbers. So we're just looking when the second derivative is undefined, in this case. Undefined. So if that's the case, well, notice we have the same old polynomial, x cubed minus 3x again. So that means x equals 0 or plus or minus 3, or square root of 3. Okay. So where do we go from here? Well, that means on our second derivative chart, we have 0, we have minus square root of 3, we have positive square root of 3. We have f double prime of x equals, so negative 2 times x squared plus 1 all over the cube root, and let's factor that denominator because we do have a 5th power going on here now. Cube root of goes x times x squared minus 3. Okay, so notice this thing does not exist at those 3 values that we listed. Alright, so let's see if we can do this one last time here. So now we want to pick something in this interval from negative infinity to negative square root of 3. Notice the numerator, regardless, is always going to be negative. Let's pick, for example, say negative 10. And if you look at the denominator, you get a negative times, you get negative 10 squared is 100 minus 3, so that's going to be, when you look at it, that's going to be positive. So negative times a positive makes a negative. You have a negative there, and you have a negative up top. So that makes this positive. That means this is concave up. Concave up, look like a cup. Okay. Negative square root of 3, 0 is our next interval. Pick, say, negative 1. Notice numerator always negative again. Negative 1 goes, we get a negative there with our first x term, and then when you square negative 1, you get positive 1 minus 3 is another negative. Negative times a negative makes a positive, but you have a negative up top. Negative divided by a positive makes a negative. In a similar manner, between 0 and the square root of 3, we can plug that in. Once again, top is negative. The denominator, pick 1 for example. You have a positive times a negative, that makes negative. Negative and negative makes a positive. So negative divided by a negative makes a positive. So last but certainly not least, let's go from square root of 3 to infinity. What happens? Pick, say, 10. Top is negative. Both parts in the bottom are positive, so that thing is negative, meaning concave down like a frown. So we are ready to draw this thing. Remember, first bit, limit as x approaches negative infinity is negative infinity. So we got to start from way down here. This is saying concave up. This is saying increasing. That's good because we're starting from negative infinity. Hopefully we are increasing. So until we get to this point, negative square root of 3. So increasing and concave up like a cup. Okay, what happens now? We're still increasing, but we're concave down like a frown until we hit that negative 1 point. So concave down, and we're increasing on this interval up until this point. So we just made the switch. Whoops. Oh, that didn't come out as planned. A little bit harder to write on these pens. Okay, there we go. So now what happens? We're still concave down, but now we start to decrease. Okay, and so we're going to decrease up until that point. Now what happens? Well, we're still decreasing, but we're concave up again. So concave up like a cup. So notice we get this little up looking thing like a cup. That concave up continues, but now we're increasing. And then finally, what happens? Well, we're increasing and we switch to concave down like a frown. So from here on out, and we go all the way up to positive infinity, and look at that. So notice our graph. You might not be able to catch this either too unless you zoom in. Notice most of the stuff that's happened is between negative square root of 3 and positive square root of 3. So that's what we're actually looking at, is trying to draw this graph just based upon the information given. And we didn't touch a calculator either. That's the beautiful thing, is we don't need a calculator, and we can now even zoom in to the part on the calculator that we need to kind of check to see where all this stuff happens. Okay, hopefully that makes sense on that problem. Now, one last piece that I kind of wanted to mention. We had questions on, so this this problem you have, suppose f of x equals x squared over 10. Use a left endpoint Riemann sum for f of x on the interval 1, 3 with, let's say, 4 rectangles. to approximate the area under the curve. So here's what happens. We get this function. We want to draw some rectangles. So let's say this is 1. Let's say that's 2. And let's say that's 3. If that's the case, and we're using 4 rectangles, what's the width of all the rectangles? So the width of the rectangles are, well, we take 3 minus 1 and we divide by 4, so that'd be 2 over 4. And so the width of each rectangle is 1/2. And so what'll happen, so we'll start at 1, we go up to the curve, left endpoint approximation means we start from the left and go right there. And so we're using that area to approximate the curve. Then the next one, we go up here, hit that curve, and then we approximate using this area. And notice each of these intervals that we're looking at, it has width 1/2 for the rectangle. And there's our 4th rectangle. So now, how do you find the area of a rectangle? So the approximation, by the way we'll write this in time, this would be the area from 1 to 3 of x squared over 10, and then we put a dx. Approximate, this really isn't going to be a great approximation. This is using 4 rectangles. What actually happens? Well, let's see. What's the width of that first rectangle? So notice the width has to be 1/2. We already talked about that. So we get 1/2 times. What's our height? Well, our height, notice it's a point on the curve, right? So it's that point on the curve. Well, what value would that be? That will correspond to f of 1. Right? So 1/2 times f of 1 plus, what's our next one? Well, the width of this rectangle is 1/2. And then what is that value? Well, we've added a 1/2 to 1. So notice that height has to be f of 1.5, or so we can do it without a calculator, f of 3/2. So we go 1/2 times f of 3/2. Okay? Plus, what's our next value? Well, you get 1/2, and then looking at this value, cross it over to what the y value is. That should be f of 2. So you get 1/2 times f of 2. Last but certainly not least, we have another width of a rectangle being 1/2. And what's our height? Once again, crossing that on over, we added another 1/2 to f of 2, so that's going to be f of 2.5 or f of 5/2, as I said, since we don't have a calculator. So 1/2 f of 5/2. Okay, so moving this on down, this is going to be approximately equal to 1/2. And notice we can factor out a 1/2 out of each of these. So pull out the 1/2, make our lives easy. And then we go, well, what's f of 1? Well, you can plug that into the equation. You get 1 squared over 10. Plus, well, what's f of 3/2? That's 3/2 squared over 10. What's f of 2? Well, that's just 2 squared over 10. And then what's f of 5 halves? That's 5 halves squared over 10. Right? And brushing that up just a little bit, we get 1 half. Common denominator is going to be 40 out of each of these. Because like 3 halves squared, that becomes 9 over 4, and the 4 drops down to make 40. So when you make this, you get 1 over 10, but you got to multiply that by 4. So 4 plus, we get 9 here. This is only over 10 right now, so you get 4 times another 4, makes 16, plus, and then our next one's 25. Okay. So what is that? Well, we get 1 half. 4 plus 9. Well, let's do this. 25 plus 16 is 41, plus another 9 is 50, plus another 4 is 54 over 40, which is the same thing. Notice the 54 and the 2, they kind of have a common value, so you can divide both of those parts by 2, you get 27 over 40. And that would be using 4 rectangles. Could we do 6 rectangles? Yeah, then each of your widths would be essentially 1/3. You could use 8 rectangles, and each of your widths would be 1/4. You could use 10 rectangles, and each of your width of your rectangles is 1/5, and so on and so forth. So at the end of the day, though, look, we had gaps. So the thing that's the problem is that this is an underestimate. In a similar manner, you could use right endpoint. So you start from the 3 and then you kind of move on over. So what would right endpoint look like? Right endpoint, if you had 1, 2, and 3, and we used 4 rectangles there, here's what your right endpoint looks like. So notice we're over on each one. So using 4 rectangles, this one was left endpoint. What would right endpoint look like? Well, right endpoint would look like essentially, so this approximation, we'd have 1/2. We get f of, notice our first one's 1.5. Our second one's f of 2. Our third one's f of 2.5. And our third one's f of 3. Oh, there we go. Let me get those values. So I have one more question here. If you have time, can I also go over the last problem of homework 19? What I do is I actually modify those problems. So if you have given me a heads up a little bit ahead of time, I probably would be able to. Let me see. I don't think I can pull that up right now. So sometimes I can do some on the fly and modify it so you can take a look. Other times it takes me a little bit more time to find a problem that is similar but a little bit different. So I'm assuming you're talking about, oh, homework 19, last problem of homework 19. Okay, let's see if I can get on there. Okay, so it's talking about, let's see if I can show it. Shoot. So you have a problem. Let's see here. My curve isn't going to be so smooth, and I'm going to make it at different points here. 2, 3, 4, 5, 6. I'm trying to make these so they're at the values that they say they are. Now obviously this is going to lead to some different answers. Let's drop that down to right here. So let's say this is your curve. Okay. So what we have here is, let me read the problem real quick. So we have a velocity function given, and we want to use a left endpoint Riemann sum to estimate the total displacement. Okay, and so it's talking about this this idea of displacement and all that stuff. So first off, this is going to be some form of velocity function, v of t. So your task is to estimate how far an object traveled during the time interval, and then let's see how many intervals we have. 0, 1, 2, 3, 4, 5, 6. So we want to estimate how far an object traveled. During the time 0 less than or equal to t less than or equal to 6. And this is a velocity function. So, and what they want us to use is this left endpoint approximation. Let me actually change the color of this. And notice this last point, even though it drops down below, it doesn't really become involved. So let me see. Sorry folks, it logged me out there. So I got to log back in to see the problem. So let's take a look here. I got it back here. So this is supposed to represent some velocity function, and granted they were given a table, but in this case rather than a table we'll have the graph and work with that. It says you decide to use a left endpoint Riemann sum to estimate the total displacement. So first off, what is displacement? What are you actually looking at? And the big things that people screw up is what's displacement versus what is distance. So distance is just basically some scalar quantity, and what you're looking at there is how much ground has been covered altogether. And what we'll have to do in that case, it's a little bit different than displacement. That's considered for those of you who have physics, it's a vector quantity, meaning like what's the overall change from our beginning position to our ending position. So that's the big difference between those two. And in terms of what we're looking at here, how are we going to find those values? Well, what we know is that the integral is what you'll hear this fancy term of 0 to 6 of v of t dt. This would be the displacement over the 6 what is it, minutes? It doesn't really say if seconds, over 6 seconds. Okay, so if that's the case, well, here's how you find it. It's not too bad. So we have -1 for our first value, we have -2 for our second value, and notice each of these intervals as listed, we're talking 1 unit. So 1, 2, 3 being here, 4, 5, and there's 6. So we should have 6 rectangles altogether, and we do. So -1 plus -2 plus keep on going, so we get what, -1 again for that shaded one. Then we get plus +1 for the next one, and plus a +2. And you might be saying, but Josh, you aren't multiplying by the width of the rectangle. Remember, the width of the rectangle in every case is 1. So this is the width, and these are your heights. So 1, 2, 3, 4, 5 for this last one. Okay, and we'll close that off. And so what do we get? Now, if you had a different width for the rectangles, you can go through those that way. Well, so you get -3, -4. So it's -1, then 4 times 1, so 4, and then the problem has it in terms of feet per second, so this would be 4 feet. Now, so this would be the displacement. How do you go through it from here? Well, distance, on the other hand, remember that's a scalar quantity, so we're always talking positive numbers. You can't have a negative distance. So every time you had a negative, basically take the absolute value of that. So you get 1 plus, you had another 2 feet, and plus another 1 feet, because all those negatives just turn to a positive value. +1, +2, +5. And so what do we have? That's 3, 4, 5, 10, 12. So your distance was 12 feet. My apologies, as I said, this was kind of asked on the fly, so I didn't have the problem written out ahead of time. But hopefully this can make sense for those of you that were working on this problem. If you have an object velocity function and you want to find its displacement, you can actually go about it and basically just take what's an integral, or just add up all the areas of those rectangles, and you have to multiply by the width if you're using the left Riemann sum. We'll learn shortcuts down the road a little later, and hopefully that'll be beneficial to you. And the big tie-in is going to be something called anti-derivatives. So basically we're working backwards all those methods of working the derivatives forward. So hopefully that makes sense on that problem. If you have any other questions, please post them in that YouTube live discussion board, and I'll be happy to answer them come the next session. Thanks for attending. Have a good night.